in the morning of today is Deliang Zhong, and he's going to talk about bootstrapping smooth line operators in Chern-Simons-Matter CFTs. Please start.
Okay, so to begin with, I would like to thank the organizers to give me the chance to speak here, and it's really a great honor. So I remember last time I was in Sao Paulo was 6 years ago in this workshop for three-point functions, and after the workshop we are watching this FIFA football game every day. So that was a really nice experience. And today, back to physics, and today I'm going to present you something that is more like a conceptual thing. There's no complicated computational techniques involved this part, and it's called and our goal is to study the smooth line operators in a simplistic conformal field theory example. It's a so-called Chern-Simons theory. And the work was done with Barak, who is currently a postdoc at EPFL, and Amit, who is a professor at Tel Aviv University. Let me start by briefly motivate why we should study these line operators. We all know in conventional QFT setup, we are more interested in study correlation functions, local operators. But recently, since the work, many people we extended the correlation function of those purely local operator to correlation functions on local operator with some defect, and in particular, we choose a strict defect in this game. The reason for studying line operators can be traced back in the early days of quantum field theory, because the original goal of Wilson and 12 to introduce this loop operator is to serve as the order parameter for the confinement or deconfinement phase transition. But today, I decided to study study such operator in generic QFT was quite hard. So I decided to go to some simpler scenario where the bulk theory is a CFT, and I also demand the line operator is also CFT. And one small comment before I start the technicalities is even in a CFT, if I have some extended operators, there will be some non-trivial RG flow along the defect. When I say conformal line operators, I mean in the bulk CFT, I put some defect and I turn on this defect RG flow, and the conformal line operators correspond to the fixed point of those line RG flows. And for extended operator, we know if I have some extended operator, for today's talk, I only focus on the simplest one, that is the line operator. So the expression value of this line operators should be a non-trivial function of the path. That's expected, but there are not so many known examples give us explicit dependence of this functional. And for example, the two famous examples like the line operator in 2D Yang-Mills theory, or some BPS Wilson loops that can be put on the two sphere on the 4D. But you know, according to the localization result, it can be reduced to some 2D Yang-Mills theory. However, for such examples, there is no actual shape dependence of the operators, and we know those operators only the expression value of those operators only depend on the area of the loop, and it is related to the fact that those loops doesn't have the cusp anomalous dimension. So our goal is to first find a theory where we can find some line operator, but there is non-trivial dependence on the shape of the operator, but yet the theory is simple enough so we can get better control of the result. And so the final motivation to study this line or extended operators, because if we have some holographic setup like in line CFTs, the holographic dual of this line operator is some string partition function with some prescribed boundary conditions set by the operator. So it's always an important quantity to study. And today I will start from the simplest but yet non-trivial example. It's called Chern-Simons-Matter theory. Let me first give a brief introduction. What is the Chern-Simons-Matter theory? For today's purpose, I will not need any Feynman diagrammatics. So we don't need to know what are the Lagrangians or this theory. But if you, for those who are really curious about what is Chern-Simons theory, it's a gauge theory. It's a gauge theory you can write down in 3D. I take a gauge group to be SUN or UN. And you can imagine you write some action like ADA plus A cube. That's where A is the connection of gauge field in 3 dimensions. And by demanding gauge invariance, you can fix the relative coefficient. So this is, roughly speaking, the only action you can write down. And the theory by itself is known to be a topological theory, and the only observable in this theory are closed Wilson loops. But if there are very rich mathematical structure if you consider correlation function between these Wilson loops, as is well known, they lead to the so-called knot polynomials. But for this today's purpose, for studying the shape dependence of path, this is not a good example because we know the Wilson loop in this Chern-Simons are topological, so there's no dependence on the shape at all. There's only the expansion value only depends on the topological class of the loops. So it's the too simple example. But yet, a non-trivial CFT can be obtained by slightly modifying this Chern-Simons theory by adding some fundamental matter field. So this is so-called Chern-Simons-Matter theory. So the idea is very simple. I have the gauge field and just minimally couple this gauge field to some fundamental, one single fundamental field transforming the fundamental representation of the gauge loop. And of course, in 3D, there are 2 ways to couple a fundamental field. You can couple to fundamental boson or fundamental fermion. But for today's purpose, the concrete realization of how this CFT is realized is not so important. Hopefully, this is a fair enough introduction. And by coupling the Chern-Simons to fundamental field, we reach a non-trivial CFT, and we can study. There are many correlation functions we can compute. In particular, we can compute a correlation function local operator, like suppose it's a fundamental scalar, like Pythagorean analog of Cornicia, or you can take many derivatives, or you can take large operator, like take many n copies of fundamental fermions. We can study this determinant-like operator. Those are interesting local operators. In addition, I can study non-local operators like Wilson loops, and so on and so forth. But as I explained before, the pure Wilson loop exponential RA is not conformal invariant, and usually, because I'm coupling to matter field, there will be non-trivial RG flow on the line. So you have to fine-tune the coefficient of this matter field on line to reach the real conformal point. But the operator I'm going to study is what we call mesonic line operator. Mesonic line operator is obtained in the very simple. For example, let me introduce a simple. Suppose I have some anti-fundamental operator denoted by O bar with some put on some space-time point x1, and I have the other operator O put on some space-time point x0. In order to maintain, because these 2 points are distinct in space-time, in order to maintain gauge invariance, the simplest way to do is just connect them by some Wilson line. And in particular, I choose this Wilson line to be the conformal Wilson line. And now I introduce some little bit notation. Just call this Wilson line W. And here I choose this X means this X is some parameterization of the line, which is not so relevant for. It's a freedom. There's a freedom to choose. And for notational, this O bar is the anti-fundamental operator. And this O is a fundamental operator, and I'll call this O and O bar the boundary operators in the theory, because they serve as the boundary of this open line operator. Okay, so I think we can go to the Bootstrap. So this is the reason to study this operator is because if you consider deformation of the closed loop, if you deform it, it will naturally lead to the product to this such a mesonic line. So we will study this operator. And the goal of this bootstrap is of course to I have to change the pen. The goal of this bootstrap program is compute this expression value of this mesonic operator with some oriented path, and solve for this 1D CFT, and this one-dimensional CFT is realized on the defect itself. And we will show in a moment that this computation can be done based on very minimal input. For example, we just assume there's a 1D CFT as it should be, and we assume a large n factorization. Is this visible, or should I change it? And the third one is the spectrum. We have to put some spectrum of the lowest lowing operator, like the lowest dimension operators. And you will see in a moment I need the two lowest laying operator spectrum in the game. And the way of computing is, let me see, strategy of computing this is to do some Taylor expansion around the straight line. Let me be precise. Suppose you have some straight line from x0 to x1, and you just consider a generic smooth curve deformation of this straight line, and with some deformation profile called V. What I do is do Taylor expansion in terms of this deformation profile over the distance. I divide by distance to make this parameter dimensionless. And philosophically, what we are doing is doing some conformal from the CFT perspective. What I'm doing is doing some one-dimensional conformal perturbation theory on the line with some effective action on the line effective action. That this effective action has some new features. Namely, it depends on the dimension for parameter V. Also, because we encounter some divergences, we have to introduce some cutoff epsilon. This is just some UV regulator to regularize the divergences. And the punchline of our result is the following. If I only demand the conformal invariance of the mesonic operator when the line is straight, and study operator insertions on this straight object, we find there's not enough constraint we cannot determine the all correlation functions on the CFT. But instead, if we study the conformal invariance of a non-straight path, we'll find this gives more constraint and leads to a unique solution. I think I said the punchline twice, so it's a good point if you want to decouple. So if you don't want to decouple, I will start to explain the details of this computation. And before doing that, I'll give you some remark. Remark is, recall before I say I can couple Chern-Simons to fundamental matter fields, and there are two ways to choose, like fundamental boson and fundamental fermion. These two theories, in 3D, it is known or conjecture that this Chern-Simons-Matter couple to boson fermion enjoys some non-perturbative strong weak duality, which is the analog of the 2D bosonization dualities. And for this whole bootstrap game, the only input is the physical information, like the operator dimensions on the line. So this bootstrap program treats both descriptions of the CFT in the same way. So so that the result is automatically invariant under this Bosonization duality. Okay, good. In order to do Bootstrap, I have to set some axioms, which is right here. But now I can be more explicit. I think this pen is not going to work. Let me change. The first, very good. The first is conform. The first axiom is a conformal invariance of the line. For example, let's consider a conformal transformation. If I have some three-dimensional conformal transformation, it maps the path x to some x tilde. This is the most general form. And both the both the endpoint fundamental operators and the line will transform accordingly to this. And the first, for the line to be conformal, we demand that the transformer line doesn't pick up any weight. So this is just the standard thing. And just say when the line transforms to a new shape, but it didn't pick up like a conformal weight, there's no additional factor of this. Some results we can immediately draw when this line is of some particular shape. For example, if the line is straight, you can imagine, suppose I have an infinite many straight line. Insert an infinite breaks the straight dimensional conformal symmetry to a subgroup, which is SL2R times U1. And this SL2R is the one-dimensional conformal group along this one-dimensional line. And we have some U1 symmetry, which is just the transverse rotation around this line. So this is the most natural way. This is immediately seen geometrically because this U1 is a rotation around this line. So as the straight line preserves this kind of symmetry, we immediately conclude that operators on the line. So line operators on the line transforms accordingly under this conformal group. So they are labeled by two quantum numbers. One is the SL2R quantum number, that is the scaling dimension. The other one is the U1 quantum number, which we call transverse spin, because it's a spin corresponding to the U1 rotation around the line. On the other hand, because boundary operators carry some dimension, so if I do a conformal transformation, they pick some weight. So to give you a flavor of what happens, so for example, let's consider some anti-fundamental SL2R primary operators of dimension delta and transverse spin minus S. Put on the x1 point. I will explain what is n1 in a moment. This is a Masonic operator. It has some paths. I have some operator with certain dimension and transverse mean. And by this conformal symmetry, we know it can first, because a boundary operator carries some weight under SL2R, we know it must transforms like primary two-point function with x to the 2 delta. And then, because this boundary operator carries some spin, I introduce some polarization vector on the boundary, and so which helps us to factor out the spin dependence. Here, the plus minus just is a notation for the local light cone coordinates in the transverse direction. So this is just the standard form of two-point function or spinning operators. The only new ingredient for the line is because I'm introducing a arbitrary line shape. So this two-point function is not just on weight times polarization, but it contains some non-trivial function of the path. And our goal is to compute this non-trivial functional based on conformal symmetry. So far, this discussion was quite general. And the second axiom I want to say is large n factorization. To further simplify the computation, large n in this context simply means if I consider a correlation function like more than one mesonic line is factorized to product of two mesonic line. So all my equations are valid up to 1 corrections. This is the first implication. Secondly, because my theory only have fundamental field, and so if I put some adjoint field, because the line is an adjoint representation. So if I want to put a joint field on the line, the only way I can construct it is to take two fundamental fields and make them adjoint. So that's a second axiom. And because it's a simplification of line operator, adjoint is made up two fundamentals. So when I insert a line operator here, the expansion value of this operator insertion factorized into two pieces. As a consequence, the crossing symmetry, this 1D crossing symmetry is trivially satisfied because you know the dependence on the distances. And the only non-trivial factor is the coefficient of this two-point function of the operator. So far, this discussion was quite general and applied to anything, and now I have to be more specific to say about the spectrum. So how much time do I have? For 20 minutes or? Oh, okay, thanks. So the third point, I start to be more specific and I start to inject a spectrum. First, I assume CPT invariance. If I have a CPT, the dimension of anti-fundamental and spin and anti-fundamental can be obtained just by the dimension of fundamental, but with its spin flipped. This is just because CPT, I take a conjugation of this operator, I flip its transverse spin. So far, it's still quite general, and my true input is I'm thinking how let me write it here. My true input is a spectrum of lowest laying primary operators on the line. And my assumption is the following. Suppose the transverse spin is smaller than 1/2. There's an operator with dimension delta. Here delta is the real parameter runs between 0 and 1. So the other operator is a transverse spin bigger than 1/2. Its dimension is 2 minus delta, and the spin is 3/2 minus delta. And I introduce. So far it looks a bit abstract. That's this notation. And first, my comment is the spin is related to dimension is just because I'm three-dimensional artifact, and in generic dimension they are independent. And at tree level, the first operator is just in the bosonic theory. You can think it's just a standard fundamental scalar phi, while the other one at the tree level is just the light cone derivative of the scalar field. And our notation to denote this operator is just the O0 and the O1, where this 0 and 1 just labels the tree level transverse spin of the operators. So that's the notation we use. And based on CPT symmetry, we can immediately imply the existence of two other operators, which is O bar naught. It can be thought as phi dagger at tree level. The other one is O bar minus 1, which is a D minus of phi dagger in the light cone coordinates. So that's our basic assumption. So based on these axioms, we without doing any computation, we can immediately get some useful information about the line. That is because delta, if delta is between 0 and 1, based on my assumption, this operator or not is the dimension, operator's lowest dimension. So, and so the simplest lowest dimension operator on the line is made by product of two O naught and its conjugate, which is just a 5 dagger, whose dimension is just in leading order in 1 over, and just is the sum of these two. So you see, because I'm in one-dimensional theory, this is a adjoint operator. If this operator is relevant, so my line will undergo some non-trivial RG flow. But on the other hand, if this operator is irrelevant, so my line will be stable. And indeed, from this simple dimension analysis, if you see if delta is between 0 and 1/2, the line is unstable. On the other hand, if it's bigger than 1/2, this 2 delta is irrelevant, so it's stable. That's our conclusion immediately from this lowest laying spectrum. And another consequences of the I think this is enough. And so far, I just set a framework of when the line is straight. And now we can start to do bootstrap to deform the line. And to remind you what we are doing, let me redraw this picture. The strategy is to start from the straight line and the tail expanding the deformation profile. And from the 1D perspective, I'm doing some conformal perturbation theory. But the standard conformal perturbation theory use some marginal parameter for expansion. Here, it's slightly different because I'm using a dimension 1 parameter to do this perturbation theory. But philosophically, it's the same thing. Okay, so to be more concrete, I start to do first order expansion. So suppose I want to do tail expansion of this operator because it consists 2 boundary and 1 line operator. So the tail expansion consists 2 parts. One is the tail expansion of the line and tail expansion of the boundary. So let's start from the line. Tail expansion of line. So suppose for this Masonic, for simplicity, I'm not draw the boundary part. If I expanding a Wilson line on top of the V to leading order, it is well known. This is just given by some operator insertion on the line. For example, we choose arbitrary parameterization of the path. And this deformation is integrated over between the endpoints. Let's choose the parameterization where endpoints correspond to s equal to 0 and 1. If you think a little bit more, you see to maintain reparameterization invariant, better to add x dot. So here I'm using a freedom of doing integration by parts to remove all the derivatives on V, like V dot, V double dot, to the boundary. So to linear order, when I expand a line, there's only operator that is proportional linear piece in V. But from this definition, we can this, and in literature, this operator called the displacement operator. It has, based on this definition, you see, for it to be a quantum operator's dimension is always 2. And it has transverse being plus minus 1 because it's contracted with some vector. And now back to our game, you see, I'm asking the following question. I have some lowest leveling spectrum. What can be the candidate operator for this displacement? And in our game, you see the displacement is quite unique. It has, in the light component, it has 2 parts. The first part is O1 times O bar naught, pictorially denoted as this. So you see O1 and O naught all has some enormous dimension and enormous spin, but if I take the product, then the enormous dimension and spin cancel, and then give some dimension 2 and spin 1 operator. Similarly, the other component of the displacement is given by the complex conjugate of this plus. It's drawing this way. It's just a complex conjugate of this operator. Importantly, in this Chern-Simons theory, this operator displacement is a chiral operator, and if you want perturbativity, it's because the equation motion, like star f equal to the matter current, and then matter current contains a derivative on both sides. So that's a read. So this is expansion of the line. We can go to expansion of boundary in a similar way. But because I use the integration part in the bulk, there's no freedom you can you can remove the derivatives on V. So in general, if it has a boundary operator, it contains some linear piece in V, a linear piece in V. But we also need to contain all possible derivatives on V. Plus, you can imagine higher order term. Here I introduce the notation dV, just a reparameterization invariant combination of V. This V dot over X dot. Such that this definition is independent of the parameterization of path you choose. But by this definition, you immediately see some the standard conformal perturbation theory still works because the dimension of V, dV, and the ddV increases because I'm taking many derivatives. Each time it increases the dimension of this expansion parameter by 1. So the operator multiplied become more and more irrelevant in this case. So it means at any given order of conformal perturbation theory, there are only finitely many operators contributing in this expansion. To give you a gut feeling of this expansion, let me do a simple exercise. Just notationally, for most of the cases, I will omit this 0 upper script, and I call this term path derivative or path variation. Let me erase the other one. But when should I stop at 12:15? In 10 minutes. Okay. So I should be more brief on this. Let me give you a gut feeling how this equation can be used. But I shouldn't erase this part. But for example, let's consider a variation of this O1 operator. By definition, this delta naught O1 is some operator whose spin is 1 unit smaller than the transfer spin is 1 unit smaller than O1, but dimension is 2 units bigger. So if you do it more, if you add, okay, unfortunately I erased the spectrum. I should keep it. I should keep it. So let me write it. So O naught has dimension delta. But they have the same normal spin. So so if you ask in your spectrum what could be the candidate operator of this operator, you find this is the only option. So the O naught is the only option. But as this two operator has opposite enormous dimension, as can be seen here. So just if spin just the O1 spin is 1 unit bigger than O naught, you have to introduce some boundary counter term to compensate for the spin, and this. Sorry, introduce some dimension for parameters compensate for the spin, and here schematically denoted as epsilon. So you can think this epsilon is on UV cutoff, and you can imagine this expansion also because it's conformal field theory. So I have primary. I can also include infinitely many descendant operators of this O naught. But when I introduce descendants by dimensional analysis, I have to compensate this by some positive power, so epsilon. So you can imagine if I expand higher enough, I'll get some operators positive power epsilon, which can be ignored in the smaller epsilon goes to 0 limit. So then you might ask what happens to what is the role of this operator, because it's depend on the cutoff. So it's and cutoff is a scheme dependent quantity, and the answer is the role is this operator is to cancel some divergences on the boundary. For example, you consider variation of this operator. It contains a single integral of some displacement near the boundary. And what we find is when displacement gets close enough to the boundary, it leads to some divergences. And these divergences have the same structure of this expansion equation. In order to maintain conformal invariance on the line, our strategy is to fine-tune the coefficient of this term, like denoted here by B naught, to cancel the divergence when the displacement go to the boundary. So that's a general strategy. After doing that, we remained with some finite equation, like given by some regularized integral. I will not, since I'm running out of time, I will not explain what is the regularization scheme we choose, but a finite integral of this type. And we have to compare it with the conformal transformation of the mesonic line. But you can play this game with translation, rotation, and special conformal. You'll find they both, for this regularized interval, they all gives to 0. So we find some consistent equation but no constraint. So you will be surprised, like I spent almost the whole talk and up to here I computed 0 equal to 0. But this is not very surprising because I'm expanding some path. And this conformal and spin weights start at second order. So that's the only lesson we have. We have to go to the next order to get more useful information. So how much time I have? 4 minutes. 4 minutes I'll be more schematic. So the non-trivial order is the second order. But schematically, I can start a second order variation of the following operator. You can imagine it contains some double integral and a single integral. I just take two and some boundary terms. The new feature as compared to the first order is at second order I can have marginal boundary term, meaning when I take two variations of the boundary operator, they can be some operator with no epsilon dependencies. And in addition, we have to regularize those intervals accordingly. But once you choose a scheme, the splitting of this term is a bit arbitrary, but the sum is well defined. And if you work hard enough, you'll find there are 14 coefficients. And the punchline of the talk is the following: if I just impose the conformal symmetry of the straight line, this conformal symmetry fixes 9 out of 14 coefficient, and there's no more constraint. And we struggle a lot to see what would be the right condition to fix a whole expression. And what we find is we have to start with some operator that is not straight, and demanding this operator transforms correctly under conformal symmetry, and expand everything to the straight path accordingly, and this will fix the remaining 6 coefficient, and that's the result. And unfortunately, I'm running out of time, so better not to speak any details about this computation, but see what are the results of the computation. What has been fixed? Like I did a second order schematically. You can ask what do I fix? The first thing is a full spectrum. For instance, before I showed you there are some operators. There's an operator with like with delta and spin equals delta 2, and we find there's an infinite tower of this operator. I start from lowest primary by demanding conformal symmetry of this line. Deduce the existence of another primary operator whose dimension spins 1 unit higher than the operator. Similarly, there's another tower of operators, which somehow. Okay, let me be more schematic. So let me don't try the execution because I don't. You find the two towers of primary operators on the line, and we can fix them dimension and the spin just by demanding a consistency with the conformal symmetry. Secondly, we can also fix the 2-point function of the displacement operator. So for example, we can imagine and compute a 2-point function of displacement normalized by the line inspection value. So it's given by, let me be more schematic. Conformal factor times a conformal factor, I mean, is a dimension 2 operator, so it has, for example, this distance to the 4th power. And some functional cross ratio is known because this correlator factorizes. The only non-trivial information is contained in this normalization of 2-point function, and we find. Let me better not to write it. So we just find this number, and then we check the answer against the perturbation theory afterwards. Moreover, we can fix. Not just the coefficient displacement operator, we can fix the coefficient of all operators because, for example, there's the tilt operator of the which has a higher spin, like 2 plus spin, and we managed to fix the coefficient to be 1/2. And the last thing is the so-called line equation of motion. Recall in the beginning we have some standard equation of motion is d plus d minus phi minus 1/2 d3 phi square. And we find the quantum version of this equation motion, like if I take a minus variation plus, is the relative coefficient in our normalization is still given by transverse derivative of the operator. So that's what we find. So since I'm running out of time, let me quickly conclude. So based on this simple analysis, expanding on a non-straight line allows us to fix the full spectrum, fix everything, fix all CFT data on the line, and by going to the next order, we managed to do some consistency check of the conformal invariant functional form. That's what we find. So finally, maybe some outlook, and just say some words about integrability. In this pure theory, we just did the expansion value of this mesonic line, and the simplest thing is to compute the connected part of this mesonic operator. But this requires more work. Secondly, we see, before I just said there's a conformal invariant function of the path, but we solve this conformal invariant function up to 3rd order in terms of deformation, but we want whether can you solve this functional in full generality. A more interesting question is the following. Based on this toy model, we see demanding a conformal symmetry on non-straight line leads to a non-trivial constraint for the operator spectrum and the CFT data on the line. Can we use these techniques to bootstrap more complicated and general CFTs? For example, to make connection with what Collier did on this bootstrapability of the line operator. Okay, thank you very much.
Questions or comments? Actually, I have one conceptual question. Here you are studying the 1D CFT on the Wilson line.
Yes.
But if you start from 3D Chern-Simons theory and dimension reduce it to 1D, then the CFT spectrum you obtain there is completely same or maybe different?
Different because this phi acquires enormous dimension from the line interaction. Just the 1D CFT data is different from 3D bulk data. For example, this operator scalar in the bulk is to leading order doesn't have enormous dimension, but on the line it acquires enormous dimension. Yep.
Any other? Okay, in view of time, let's thank the speaker.
Thank you.
Okay, so I'm not sure if everyone managed to try out